We are solving question 24 of GATE 2012 chemical engineering paper, and this is related to instrumentation and process control. The question is, a thermometer initially at 100 degrees Celsius is dipped at time t equal to 0 into an oil bath maintained at 150 degrees Celsius. If the recorded temperature is 130 degrees Celsius after 1 minute, then the time constant of the thermometer in minute is dash. So in this given question, we have been given a thermometer and at time equal to 0, that is at time equal to t equal to 0, the temperature that is being shown or recorded by the thermometer is 100 degrees Celsius. So that is, we can write it as y of 0 is equal to 100 degrees Celsius. Then the oil bath is maintained at 150 degrees Celsius. That is right. Oil bath is maintained at 150 degrees Celsius, and if the recorded temperature is 130 degrees Celsius after 1 minute, that is at t is equal to 1 minute, y of 1 is 130 degrees Celsius, then the time constant of the thermometer in minute is dash. So time constant we have to find. So we know that thermometer we can consider it as first order system. So by first order system we basically mean that the model equations of corresponding to this thermometer can be written in the form of tau of dy by dt plus y is equal to kp into x, where x is a function of time. So this time is time constant, y you can call it as output, x are my process inputs, and kp is the process gain. And if we have to write this in terms of this transfer function, that is a transfer function of thermometer, you can write it as g of s, which is y of s upon x of x, that is output upon input, is equal to, for first order system, we can write it as kp upon tau s plus 1. And that is, we can write it as ys is equal to kp upon tau s plus 1 into xs. Now here we can see that initially the temperature was maintained at 100 degrees Celsius, and later on so if we draw a diagram over here with time, so initially let's say the temperature is constant at 100 degrees Celsius, then later on it is dipped into an oil bath maintained at 150 degrees Celsius, shown over here. So that is, this can be shown that over here the temperature is 150 degrees Celsius. So over the time, the thermometer will try to record this 150 degrees Celsius. So based on this time constant and Kp, it will show this part, this kind of trajectory, where this is 150 degrees Celsius, and these are the actual temperature recorded by the thermometer. That is basically Y. This you can call it as Y. And here we have been given, if let's consider this as 0 minute and this as 1 minute. And at 1 minute we have been given that the recorded temperature is 130 degrees Celsius. So this is 130 degrees Celsius. And we have to find the time constant of the thermometer. So tau, we define it as time taken by the system to reach 63.2% of that output variable. So basically time taken by the system to reach of this 62.3% of the delta t, that is 50 into 0.632 plus 100. So how much time is taken by the system to reach that value is defined as time constant. So if we had to convert this, so yes, in here we can see that we are giving a step input to the system. So initially the system was 100 degrees Celsius, and then we increased the temperature of the surrounding to 150 degrees Celsius. That is, we are giving a step input of magnitude 50 degrees Celsius. Okay, so that is, we can write it that as Kp is equal to 50 degrees Celsius. And if you have to convert this into this time domain to find the temperature of the thermometer at 1 minute, no, to find, yes, basically to relate the temperature, to find the temperature at any given time, we need to write it in terms of time. So you can take the inverse Laplace of this term and write this at y of t is equal to Kp into 1 minus e raised to minus 1 upon tau. So in this case, since we were giving a step input, so our excess transfer function would become a by s, where a is in this case this 50. It will become 50 upon s. So you can also write this as a to 1 minus t upon tau, where a is this difference. Okay, so now let's use this equation. So y of t, that is temperature at any time interval, is given as a to 1 minus e raised to minus of t upon tau. A is 50, 1 minus e raised to t upon tau is equal to y of t, and y of t we can write it as y minus ys. So these are small y's. So basically these are the deviation variables, to 15 to 1 minus of e raised to t upon tau. Now at t equal to 1 minute, we have the temperature as 130 degrees Celsius, and the initial steady state of that system was 100 degrees Celsius, is equal to 50 into 1 minus e raised to 1 minute upon tau. So this you can write it as 30 upon 50. So it will become 0.6 is equal to e raised to minus 1 upon tau will be 0.4, and then you can take the log of this term and you will get minus 1 upon tau is equal to point minus of 0.9163. So this will give us tau is equal to 1.091 minutes. So the time constant for the thermometer in the given question is 1.091 minutes, and from the given option we can select option D.